And let's take a look at some more scenarios here. In fact, this first one, we're going to go through the full routine of getting the equation of the tangent line out. So we're looking for y equals mx plus b. But to start that, we're going to start by finding m, which would be evaluating dy dx at that point 2, 3. So where we're headed is to get m. We're going to evaluate dy dx at the point 2, 3. So with that, we need to find dy dx. So we're going to take our equation, it's x cubed plus y cubed equals 6xy minus 1, and we're going to take the derivative with respect to x of both sides. So we'll have the derivative with respect to x of x cubed plus derivative with respect to x of y cubed equals derivative with respect to x of 6xy minus derivative with respect to x of 1. Okay, so let's go through our pieces here. So derivative with respect to x of x cubed, we just follow our rules, and that would be 3x squared. Plus derivative with respect to x of y cubed. So again, our outside function is the exponent of 3, so what we would do is take the derivative as we usually would, 3y squared, but because of the chain rule, then we would have the derivative of our inside function, which is y, and that leaves us with dy dx equals. Here, we're going to need the product rule. So, because we have x and y multiplying with each other, and I'm going to write this all out. Sorry if this is tedious, but I hope it helps in terms of clarity. So we're going to have derivative of one piece. So let's call that 6x. We'll put together and then times y, and then we'll add, keeping 6x the same, times the derivative with respect to x of y. So that's our product rule right there. Derivative of one times the original of the other, plus, and then swapping it around. And then we have minus the derivative with respect to x of just a constant of 1, which is 0. So I'm going to go ahead and just take that away. But there is a plus, or rather a minus 0 out here, but that just disappears. We don't want to forget that last derivative, but it doesn't add much in terms of our equation. Okay, so I'm not quite done taking the derivative yet. So I'm going to have one more step taking derivatives, 3y squared dy dx equals, so derivative of 6x will just be 6, so we'll have a 6y plus 6x times derivative of y with respect to x is dy dx. Okay, so derivatives are done. Then what I do is I go looking for where is dy dx. And what I want to do is have those together on one side of the equation. So what I will do is, I'm going to subtract 6x dy dx from both sides. And then that'll group everything on the left-hand side. So that means I also want to get this 3x squared away from that. So I'm going to subtract 3x squared from both sides. So what that'll leave me with is a 3y squared dy dx minus 6x dy dx on the left-hand side equals, and on the right-hand side I'll have 6y minus 3x squared. And now we have dy dx together on one side of the equation, so we can factor it out. So dy dx factored out will leave us with a 3y squared minus 6x equals 6y minus 3x squared. And our last step is to divide both sides. So we're getting dy dx is equal to, and in the numerator, 6y minus 3x squared over 3y squared minus 6x. Okay, So that was our process for taking the derivative using implicit differentiation. And now what we want to do is go back, because our whole thing is to get the equation of the tangent line. So we're going to start by finding our slope, which is to evaluate dy dx at that coordinate, which they gave us is 2, 3. So what we're going to do is take that equation we just found and plug in 2 and 3. So we're going to have 6 times y, which is 3, minus 3 times x squared, so a 2 squared, over 3 times y squared, so 3 times 3 squared, minus 6 times x, which is 2. And we're going to go ahead and simplify that down. So let's see, in 18 minus 12 over 27 minus 12. So a 6 over 15, so a 2/5. Something I just thought of that doesn't matter too much. Really, the simplified form of this, there is a common factor of 3, and that is important to notice here, that we'd have 2y minus x squared over y squared minus 2x. And in terms of this scenario where we're going to be plugging in, it doesn't particularly matter. If we were looking for the simplified form of the derivative, then we would definitely want this 2y minus x squared over y squared minus 2x. But in this case, we end up plugging in and it all kind of works out for our equation of the line. So for this scenario where we're plugging in, it doesn't matter too much to have the completely simplified form. But if the goal is to solve for dy dx, we would want to take the steps of simplifying completely. Okay, so we found our slope. Y equals 2/5 x plus b. And let's go ahead and plug in our coordinate 2, 3. So 3 equals 2/5 times 2 plus b. And then we have some fraction math to do. So b is equal to 3 minus 4/5, or 15/5 minus 4/5. So 11/5. So our equation, y equals 2/5 x plus 11/5. Again, you can check these out. You can graph this into Desmos, plug in the equation of the line, and check that it is in fact making a nice tangent line at the coordinate 2, 3, which would be right there. So it should look like something like that. Okay, our next equation here is y squared equals 4e to the xy minus 2. And we're going to take the derivative at the point -1, -2, so that we could get the equation of the tangent line. Okay, so derivative with respect to x of both sides. So exponent of 2 would give us 2 times y, and then we would have derivative of the inside function, so dy dx equals, and here we're going to have some chain rule with an inside function of xy minus 2, and at the outside we have a 4 with a base e. So base e, it just stays the same, so we'd have 4 times e to the xy minus 2, but then I need to multiply that with the derivative with respect to x of xy minus 2. Okay, so left-hand side, 2y times dy dx. Here we have a 4e xy minus 2. And taking the derivative here, we're going to have product rule, which means we'll take the derivative of x, which is just 1, so that'll be a 1 times y, plus keeping x and the derivative of y would give us a dy dx. And then derivative of the -2 just turns into a 0. And then what we need to do is distribute that exponential piece. then we could start grouping things together. So let's see, 4 times y e to the xy minus 2 plus 4x e to the xy minus 2 times dy dx. Okay, so there's a dy dx. Here's another one, so I want those together on one side of the equation. So I'm going to have 2y dy dx minus the 4x e to the xy minus 2 dy dx. And then alone on the right-hand side will be the 4y e to the xy minus 2. Factor out. So I'll leave us with a 2y minus 4x e to the xy minus 2. And then divide that away. So we're going to get dy dx. In the numerator, we'll have 4y e to the xy minus 2 over, and then 2y minus 4x e to the xy minus 2. Okay, so from there, we're going to evaluate this at the coordinate -1, -2. So let's even, since we have this graph here, let's take a look at where that is. So we're right there. So it looks like it might be vertical. It could also maybe be like a little negative. We'll see as we plug this in. So for the slope of the tangent line, I'm going to evaluate dy dx at that coordinate -1, -2. So that's going to look like 4 times a -2 e to the -1 times -2 minus 2 over 2 times y, which is a 2 times -2 minus 4 times -1 e to the -1 times -2 minus 2. So what is nice is those exponents turn into 0. So really e to 0 is just going to turn into a 1. So we have a 4 times -2 over a -4 plus 4, which is going to be a -8 over 0, which means our slope does not exist. So what that's telling me is that at that point, we are getting a perfectly vertical line. So the equation of my tangent line is going to be x equals, and then using my x coordinate of -1, that will be the vertical line. That is the equation of the tangent line. So when you get through this process and the slope does not exist, check the graph to see if you're getting a vertical line coming through, because you will have an equation of the tangent line even if the slope does not exist. Okay, last example here, one more with implicit differentiation, a little word problem here. So we have a simple video game, and we have a rocket travels in an elliptical orbit whose path is described by the equation 4x squared plus 25y squared equals 100. In fact, let's get a visual going here. Let's go ahead and graph that so we can see what this rocket is doing. So 4x squared, 25y squared equals 100. Making sure I typed it all in correctly. All right, there's our ellipse that the rocket is traveling on. The rocket can fire missiles along lines tangent to the path. So as long as it's tangent, it can be shooting rockets in that direction. The object of the game is to destroy an oncoming asteroid traveling along the positive x-axis towards 0, 0. So if we're on the x-axis down here, it's that the asteroid would be coming in this direction. And what we need to do is use those tangent lines to try to shoot a missile and destroy the asteroid. So if the rocket fires a missile when it is located at 3/8. So let's go ahead and see where that's happening. So right when we're there, where will it intersect with the x-axis? So what we're doing is we want to graph the tangent line, and then we want to see where is the x-intercept of that line, because then that'll tell us when it needs to fire to hit the asteroid. So what we're going to do here is get the equation of the tangent line at that point, and then using that line, look at where x equals 0. Sorry, yeah. Where y equals 0. That'll tell us the value of x where it'll intersect. Okay, so starting to find our equation of the tangent line, let's find slope by taking the derivative. So 4x squared plus 25y squared equals 100. And we're going to take the derivative with respect to x of both sides. Now, with this one, I'm just going to walk you through how I go through this a little bit more quickly. But again, writing out steps is always a good idea. But what I'm thinking is, okay, we'll have this derivative of 4x squared, and that'll just be our standard following the rules. So that would be 8 times x plus taking the derivative here, and what I'm just going to pay attention to is because I'm working with y, I should end up with a dy dx. So first I follow the rules, so I'll have a 25 times 2 is 50 times y, and then because this is our special case, we'll also have the derivative of y, which is dy dx, equals derivative with respect to x of 100 is 0. And then we solve for dy dx. So subtract from both sides and divide. So we're getting a negative 8x over 50 times y. All right. So there's our equation for the slope. So what we want to do is evaluate that. So evaluate dy dx at the point 3/8. So plugging in, we'll have negative 8 times 3 over 50 times 8/5, which is a negative 24 over 80, which should be a negative 3/10. Let's go ahead with decimals here. Let's call that a negative 0.3. So our equation is a y equals negative 0.3x plus b. And to find b, let's go ahead and plug in 8/5 equals negative 0.3 times 3 plus b. And solving for b, we should get a 2.5. So our equation of the line is y equals negative 0.3x plus 2.5. And let's see how that looks. So y equals negative 0.3x plus a 2.5. And there's our tangent line to our ellipse. And what we're going to look for is this coordinate right here, that 8.333. Which we can see right there, but let's solve for it algebraically by plugging in y equals 0. So to get the x-intercept, we're going to be solving 0 equals negative 0.3x plus 2.5. So subtract 2.5 from both sides. Divide by negative 0.3. And that should get us to our 8.333. So that tells us if the rocket is located at that point 3/8, it would want to shoot and it would be hitting at 8.333. So if the asteroid's at that location, it'll hit it. If the asteroid's at any other location, it will not hit the asteroid. Okay, so there's our implicit differentiation. You get lots of practice with these in the participation packet. But once you get the flow of it, it's pretty nice. And you get to look at it. I like them particularly because we get to look at these interesting types of equations and graphs that aren't typical for our standard functions.